Okay, welcome everyone. So in this video, I want to continue talking about inner product spaces, and we're going to look at inner product spaces other than just Rn with the usual dot product. So in this case, I want to consider the vector space that we're going to denote with a script C from the closed interval a to b. So the objects in this vector space are continuous functions on the closed interval from a to b. And so defining the typical addition of functions and multiplication of a function by a scalar, we can verify that this set of functions with those standard operations actually forms a vector space. And so if we define the following function, that for any two continuous functions f and g in this vector space, we are going to define the inner product of f with g as the definite integral of the product of f and g evaluated over the limits from a up to b. So this is going to be well defined. If f is continuous and g is continuous, then the product f times g is continuous, and therefore we can integrate continuous functions. So let's verify that this is indeed an inner product, and that gives us a way of defining distances and angles in our vector space of continuous functions from a to b. So the first property that we would need to check is whether the inner product f with g is equal to the inner product of g with f. Can we switch the order around? And certainly we can. So by the way we've defined this function, the inner product of f and g is the integral from a to b of f times g. And we can just change the order of that product. That's going to equal the integral from a to b of g times f. And that by definition is the inner product of g with f. So we can change the order around without changing the value of the inner product. Next, let's check the property that says if I take two continuous functions and add them, f and h, and then take the inner product with g, is that going to be the same thing as taking the sum of the inner product of f and g with the inner product of h with g? And here we can again do a little bit of rearranging of terms and regrouping our integrals. So we can take the f times the g plus the h times the g. We cannot split up products inside of integrals, but we can break up sums. So now that I've written the integrand inside of here as f times g plus h times g, we can split that sum up. So we have the integral from a to b of f times g plus the integral from a to b of h times g. So that exactly gives me the inner product of f and g plus the inner product of h and g. So the second property checks out. For the third property, this is going to follow pretty quickly because we can pull out scalar multiplication from inside a definite integral. We can pull that scalar out. So taking the inner product of scalar c times f with g, we would integrate from a to b c times f times g. We can't break up expressions that have the t in them. If we have a product, we can't break up products inside the integral, except we can pull out constant multiples. So that c doesn't depend on t. We can pull it out from the definite integral, and therefore we've written this as c times the inner product of f and g. So that property that we can pull scalar multiples outside the inner product holds. And we've got one more property to go, which says if I take the inner product of f with itself, I need to get something which is greater than or equal to 0. So if I integrate from a to b f of t squared is a non-negative expression. So if we take the definite integral of a function which never goes below the t-axis, we are guaranteed to get something which is greater than or equal to 0. Since that function is going to be at least on or above the t-axis. So that definite integral is going to calculate an area, and that area has to be entirely above the t-axis. So this is going to be something greater than or equal to 0. And the only way that we get an area of 0 is if this function f of t was equal to 0 always. So that proves the fourth and final property required for this to be an inner product space, and that is the inner product of f with itself is going to equal 0 only if the function f is equal to 0 everywhere. So now that we've got an inner product that we've defined on this vector space, we can calculate lengths and we can determine whether two vectors, whether two continuous functions are orthogonal to each other. So let's take a look at that on the next slide. Okay, so let's continue working with this vector space of continuous functions. And here we're going to take a look at the set of continuous functions over the closed interval from 0 to 1. And we are going to put an inner product on this vector space where we're going to define the inner product of f and g as the definite integral from a to b of the product of f and g. So this is a very standard inner product to put on this function space. And I should note that this function space, this vector space of continuous functions, is infinitely dimensional. So if we want to construct a basis for this vector space, we need an infinite number of elements in our basis. But that's another story. What we're asking here is, let me see whether the vector 1 plus t squared, is that orthogonal to the vector 4t? So both of these functions are continuous from 0 to 1, but I want to be really clear that this vector space is not restricted to just polynomials. We could have things like e to the t, cosine of t, all sorts of other functions as long as they're continuous on the closed interval from 0 to 1. But to make the calculations a little bit less overwhelming, we're going to pick two polynomials, and I want to determine whether these are orthogonal. So by definition, they're going to be orthogonal if the inner product of 1 plus t squared with 4t is equal to 0. So here we define this inner product as saying we're going to take the product of 1 plus t squared and 4t and then integrate that from 0 to 1. So let's just distribute terms first of all. So this is equal to 4t plus 4t cubed. And now when we integrate that with respect to t, integrating 4t gives me 2t squared. Integrating 4t cubed gives me t to the fourth. And it's a definite integral, so we're going to evaluate that at the limits from t equals 0 up to t equals 1. So evaluating at 1 gives me 2 plus 1 of 3, and evaluating at 0 gives me 0. So the inner product of these two vectors, these two continuous functions, gives me 3. So that tells me that these two vectors are not orthogonal to each other.